All right, now we're going to look at powers of complex numbers using what we're going to find out is called DeMoivre's theorem. We've already talked about DeMoivre before. So we want to understand how we can use his theorem to help us find powers of complex numbers very easily when they are in trig form. So first, let's recall our trig form. So I know if z equals r cosine theta plus I sine theta, and this would be the same z equals a plus bi, right? So this is standard form. This is trig form. Okay, what is z squared then? Well, let's look at z squared in standard form. So z squared would be a plus bi squared. So then this becomes z squared equals a plus I times a plus bi. And if we multiply this out, we end up with a squared plus 2abi plus b squared I squared. But then let's simplify that. We know I squared is -1. So I end up with z squared equals a squared minus b squared plus 2abi. So that would be z squared in standard form. Now that wasn't that bad, but as you can see already, what's going to happen when we have z cubed, z to the fourth, z to the fifth, this is going to become a pain, right? So what about in trig form? Well, I know that z squared, we learned this, is z times z. So we learned this in our previous section, where if I multiply two complex numbers in trig form, then all I have to do is multiply their r values and add their angles. So I know z squared is going to be r times r cosine of theta plus theta plus I sine of theta plus theta. Or a simpler way to write that is I end up with z squared is r squared cosine of 2 theta plus I sine of 2 theta. The point is, notice that that was pretty easy to do. Wasn't that hard in standard form, but still the trig form was easier, and especially when we get to z cubed, trig forms can be even easier, because I know that z cubed is z squared times z. So I can just follow the pattern again, and I can say that z cubed is going to be r squared times r, because I know z squared is r squared, times cosine of 2 theta plus I sine of 2 theta plus theta. So all I'm using there is just my properties for products of complex numbers in trig form that we learned about in the last section. And now I'm going to simplify again. And we end up with z cubed equals r cubed cosine of 3 theta plus I sine of 3 theta. So in doing just those two problems of z squared and z cubed, you hopefully are noticing a little bit of a pattern, and that's what actually leads us to DeMoivre's theorem, which says in general, if we have some complex number in standard form, a plus bi to the nth power, if we write it in trig form, then z to the nth power is going to be r to the nth times cosine of n times theta plus I sine of n times theta. In shorthand, that would be r to the nth cis of n theta. And so again, we can see that real quick here with z cubed, that this was r cubed cosine of 3 theta, I sine of 3 theta, and those 3's are all because this was to the third power. So this is our DeMoivre's theorem. And again, this is very helpful when we are raising complex numbers to very large powers. So I want you to try this. Evaluate and write your answer in standard form. We're doing 3 cosine of 330 plus I sine of 330 to the fourth power. So evaluate it in trig form, and then I want you to rewrite your answer in standard form, or convert your answer to standard form. So I want you to try this on your own. Pause the video, unpause when you're ready to check. All right, hopefully you got negative 81 over 2 minus 81 root 3 over 2i. That's our standard form. But how do we come about that? Well, first, again, we're going to actually do the power in trig form. So I know that this is going to be 3 to the fourth cosine of 4 times 330 plus I sine of 4 times 330. Well, what's 4 times 330? That's 1320. I don't want to use 1320 as an angle because I don't know what the sine of 1320 is, so I'm going to think in terms of coterminal angles. So if I subtract 360, subtract 360, subtract 360, subtract 360, and I get to something between 0 and 360, I get 240 degrees. I know what the sine of 240 degrees is, and I know what the cosine of 240 degrees is. Cosine of 240 degrees is negative 1/2. The sine of 240 degrees is negative root 3 over 2. So that's where that minus came from. So then the only thing I have left to do is distribute the 81 to write this in the standard form of a complex number. So again, this was much easier to do in trig form if I had first figured out what is the cosine of 330, the sine of 330, distributed the 3, and then raised that quantity to the fourth power. That would have been a mess. Could I do it? Absolutely. But it would have been a lot more work than what I did here. Next one. So here we're given the initial complex number in standard form. So keep in mind here, when we're saying this, the complex number that we're dealing with, z equals negative root 2 over 2 plus root 2 over 2i. That's our complex number, okay? And then we're going to raise that to the 12th power. So in order to do this, first you want to convert it to trig form. So convert this to trig form, raise it to the 12th power, and then convert it back to standard form. So pause the video, do that, unpause when you're ready to check your answer. All right, so over here you got the answer is actually just negative 1. If you wrote negative 1 plus 0i, that's fine. But negative 1 is what we get. Okay, so how do we do that? So again, here was my complex number, negative root 2 over 2 plus root 2 over 2i. So I need to figure out, okay, what is the r value? R is the square root of a squared plus b squared. R came out to be 1. What is theta? So this is where I had to think about, okay, if I go left root 2 over 2, and then I go up root 2 over 2, I'm in quadrant 2. So that's going to help me in terms of figuring out what angle do I have. And I know that tan theta is root 2 over 2 over negative root 2 over 2, which is negative 1. So at what angle is tangent negative 1, but in the second quadrant? That's going to be 135 degrees. Again, you could work in radians if you want. This is your choice in this case because we're only temporarily using the trig form. So it's up to you whether you want to work in radians or degrees. I chose degrees. So theta is 135, so I can write the trig form of the complex number. Z equals 1 cosine 135 plus I sine 135. Now I raise that to the 12th power, so z to the 12th is 1 to the 12th, cosine of 12 times 135 plus I sine of 12 times 135. 1 to the 12th is 1. 12 times 135 is 1620. So I get cosine 1620 plus I sine 1620. But again, in terms of finding coterminal angles, if I just keep subtracting 360, I realize that 1620 and 180 degrees are coterminal angles. The cosine of 180 degrees is negative 1. The sine of 180 degrees is 0. So when I convert this back to standard form, I end up with just negative 1. Or like I said, negative 1 plus 0i would be acceptable as well. Okay, so what we want to get from this is that DeMoivre's theorem allows us to easily find powers of complex numbers when they're in trig form. So anytime you're trying to find powers of complex numbers, whether you're given the complex number in standard form or trig form, convert it to trig form, find the power, and then convert it back to standard form if you need to for your answer.